Welcome to the SAR channel, where sound and audio are demystified. The goal of speech coding is to convert speech into a format that can be sent efficiently over communication systems. A speech codec must make the speech easy to understand while compressing the signal to use fewer bits. Although speech and music codecs share similar goals, their designs are quite different. Unlike music codecs, speech codecs use models that focus on the unique features of the human voice. This makes them work very well for speech, but not as well for other types of sounds. Because most transmission channels have limited bit rates, speech coding faces many challenges. Besides keeping speech clear and the bit rate low, a codec must handle poor signal conditions, use limited processing power, and have low delay for real-time communication. Wireless systems also add difficulties because they often suffer from more transmission errors. A good speech codec must make speech easy to understand. This means listeners should clearly hear the words, recognize who is speaking, and notice their tone and emotion. Besides being clear, the sound should also be natural and pleasant. Many codecs use perceptual enhancement algorithms to improve how the speech sounds, often applied during decoding as post-processing. The quality of speech codecs is usually tested by listening to how people perceive them. A reliable speech codec must work well even in noisy environments or when the microphone distorts the sound. It should perform well for all types of speakers, men, women, and children, and across different languages. Speech codecs should also handle simple non-speech sounds, such as telephone tones or background music, at least without unpleasant noise or artifacts. A codec should not be too complex to run. Lower algorithmic complexity means less power use and lower cost. Some advanced methods, like analysis by synthesis or added features such as echo cancellation, increase processing demands. So a good codec should offer strong performance while requiring little computing power and memory. A speech codec should also keep delay to a minimum. Every codec causes some delay while processing signals, but in real-time communication, this delay must be very short. Delay mainly comes from buffering input samples and frame-based processing. Generally, greater delay allows better compression, so designers must balance the two. In offline uses like voicemail, delay is less important. The codec must also handle transmission errors that can cause unwanted clicks or pops. Forward error correction helps reduce these problems but adds extra data, delay, and bit rate. Mobile systems often use unequal error protection, giving more correction to the most important data and less to the rest. This ensures that even with errors, speech remains understandable. Because transmission channels have limited bit rates, speech codecs must use lossy compression to reduce data size. Many codecs use models based on how human speech is produced. Air from the lungs acts as an excitation signal, while the vocal tract shapes it like a filter. Speech is a mix of voiced sounds, regular pulses, unvoiced sounds, random noise, or both. The decoder rebuilds speech from parameters that describe these two parts over time. Speech and music codecs share the same goal, to deliver high-quality sound using as few bits as possible, but they use very different methods. Speech codecs often model how the human voice works, while music codecs like MP3 model how the human ear hears sound. Most music systems use PCM or perceptual coding methods such as MP3. These are called waveform codecs because they directly code the shape of the audio waveform. Since music waveforms are complex and unpredictable, the codec must be flexible enough to handle any possible shape. Waveform codecs represent sound as quantized samples or frequency coefficients and usually need higher bit rates to keep good quality. ADPCM is a type of waveform codec that uses predictive coding and is common in landline telephones. Because it does not model the voice, it can handle both speech and music. However, it is less efficient and needs a higher bit rate than speech codecs that use voice modeling. Some older systems use delta modulation, another predictive method that also does not use source modeling. More advanced speech codecs, used in mobile phones and VoIP, achieve much lower bit rates by modeling how speech is produced. These codecs analyze the vocal system and transmit data as parameters describing the speech model instead of the full waveform. This approach is called source coding. It differs from perceptual coding, used in music, which focuses on what the ear can hear rather than how the sound is made. Speech coding focuses on encoding and decoding a specific sound source, the human voice. Because speech signals come only from the vocal system, they are more predictable and can be represented by fewer parameters. Parametric source codecs describe speech using a small set of parameters that capture the key features of the excitation signal and vocal filter. The encoder extracts these parameters, and the decoder uses them to recreate the speech. Linear prediction is the main technique used here, allowing very low bit rates, though higher rates don't always mean better sound quality. Hybrid codecs combine ideas from both waveform and source coding. They use a speech model to estimate parameters of the voice source and then reconstruct a waveform close to the original. An example is the CELP family of codecs, which are widely used and operate at medium bit rates. Finally, multi-mode codecs can switch between different coding methods depending on the sound type or network conditions. Control data tells the decoder which mode is used. Although each mode may have a fixed bit rate, switching between them creates an overall variable bit rate, improving efficiency and lowering average data use. Speech coding is different from music coding because all speech sounds come from one source, the human vocal system, while music comes from many instruments. A music codec must handle many types of signals, but a speech codec only needs to deal with one. This consistency makes it possible to use source coding, which models how the voice produces sound. To understand speech codecs, it helps to know how the vocal tract works. Speech, like all sound, is simply air pressure changing over time. Air from the lungs moves through the body and out of the mouth or nose, shaped by different parts of the vocal system. In reality, this process is quite complex. Making speech requires precise control of airflow using many organs that together act as a time-varying acoustic filter. The vocal system starts with air pushed up by the diaphragm and lungs. This air passes through the trachea and over the vocal cords, or vocal folds, in the larynx located at the Adam's apple. When the vocal cords vibrate, rapidly opening and closing, they create a noise-like excitation signal. The opening between them, called the glottis, can either block air to form pulses or let it flow freely. The tightness of the vocal cords controls the pitch. The velum directs airflow into the nasal cavity. The air then moves through the mouth and nose, where the tongue, lips, teeth, and jaw shape it by creating constrictions that change air pressure. The mouth and nasal cavities also act as resonators, emphasizing certain frequencies called formant frequencies, which depend on the vocal tract's shape and position. Speech sounds are grouped into voiced and unvoiced types. Voiced sounds come from the vibration of the vocal cords, creating regular pulses and a clear pitch. Their fundamental frequency is about 50 to 250 Hz for men and 150 to 500 Hz for women. Vowels and some consonants are voiced. Unvoiced sounds happen when air flows continuously past still vocal cords, creating noisy, irregular turbulence. Examples include S, F, and P, known as fricatives. Brief bursts of air, called plosives or stop consonants, may be voiced or unvoiced. The transitions between voiced and unvoiced sounds can also be hard to define. Although human speech covers a wide range of frequencies, most communication systems transmit only from 300 Hz to 3,400 Hz, which is still enough for clear and understandable speech. The source filter model used in many speech codecs imitates how the human vocal tract works, allowing it to create sounds similar to speech. Because it is designed for voice, this model does not perform well with music signals. The model is based on the idea that the vocal tract acts like a filter that changes over time, shaping the sound's frequency content to form different speech sounds. Although many speech codecs use this same basic idea, they differ in how they calculate and encode the speech parameters for transmission. In this model, the vocal cords are represented as an excitation signal, a sound with an even frequency spectrum. The various phonemes, basic speech sounds, are formed by how this excitation signal is filtered by the vocal tract. For voiced sounds like vowels, the excitation is periodic and made up of regularly spaced harmonics, appearing as repeated pulses over time. For unvoiced sounds such as F, S, and esh, the excitation is more like white noise. For voiced fricatives like V and Z, the excitation combines both harmonic and noise components. The channel vocoder, created in 1939, was one of the first types of speech codecs, often called vocoders or voice coders. It showed that speech could be efficiently represented using its frequency components. A more advanced version, the Formant vocoder, made this process more efficient. Instead of coding all the frequency details in the speech signal, it focuses only on the most important parts. The human vocal tract naturally resonates at certain frequencies called formants, which appear as peaks in the sound spectrum. Usually there are about 3 major formants below 3 kHz. The encoder detects these formants in each short frame of speech by tracking the peaks in the spectral envelope, then codes their frequencies and amplitudes. Like channel vocoders, it also transmits information about pitch and voicing. Sinusoidal codecs use a different approach called sinusoidal modeling. They represent speech as a sum of many waves whose amplitude, frequency, and phase are adjusted over time to match the original speech signal. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Speech waveforms are generally simple. They consist of repeating tones, the fundamental frequencies, mixed with short bursts of noise. They can be modeled as pulses, noise, or both. In speech coding, the sound is treated as the result of an input excitation signal passing through the vocal tract filter. By sending only the parameters that describe this excitation and filtering process, the decoder can recreate the speech signal. Speech changes over time, and these changes carry meaning. While sounds vary quickly between words and phonemes, within short time spans, speech remains fairly stable. This is called quasi-stationary. Because of this, most speech codecs process short time frames and use predictive coding to remove redundant data. In predictive coding, each new sample is estimated using previous samples. The difference between the actual and predicted value is then quantized, which uses fewer bits than coding the full signal. The decoder rebuilds the signal using these difference values, as done in ADP-CM codecs. At lower bit rates, instead of coding these differences directly, it's more efficient to send an excitation signal that the decoder uses to generate a signal close to the original. This approach is the basis of linear prediction. A short-term predictor models the spectral envelope of speech, the vocal tract, and a long-term predictor models its fine structure, pitch, or periodicity. Some designs simplify or rearrange these predictors depending on their goal. Both predictors adapt continuously to match the changing speech signal, adjusting their filter coefficients for better accuracy. Since the vocal tract changes shape slowly, these updates don't need to happen too quickly. To avoid audible glitches from sudden filter changes, the codec smoothly transitions between values using interpolation. A long-term prediction filter is often used in code-excited codecs to represent the periodic part of the excitation. Since small codebooks can't capture this repetition efficiently, the predictor's parameters are estimated by analyzing the signal to find the best delay value. Some codecs replace this filter with an adaptive codebook that stores earlier excitation data. The encoder picks the codebook entry that minimizes the difference between the original and reconstructed sound. This is known as analysis by synthesis. The difference, or error, between the original and reconstructed signal is minimized using criteria like mean squared error. At normal bit rates, this produces evenly distributed quantization noise, but at low bit rates, noise increases. To make noise less noticeable, codecs use noise shaping based on psychoacoustic masking, even if it increases the overall error mathematically. In code-excited or vector-excited codecs, both the encoder and decoder share a codebook of possible excitation sequences. The encoder simply sends the index of the best matching entry, chosen to minimize weighted error. This makes the process highly efficient. Some codecs also use a post filter after decoding to enhance important speech frequencies, formants, improving clarity and reducing audible noise. However, these filters can distort the signal and don't work well for non-speech sounds. Linear predictive coding, or LPC, is a common and efficient method for speech compression. It works well at low bit rates and doesn't require heavy processing power. LPC analyzes speech using a source filter model that mimics the human vocal system. It predicts each new speech sample from a weighted sum of earlier samples, reducing repeated information between them. In a basic LPC codec, the encoder studies short frames of speech and calculates filter coefficients that describe the shape of the vocal tract. These coefficients, along with a scale factor, are sent to the decoder. The decoder then creates white noise, scales it, and filters it using the received coefficients. This process repeats for each frame, producing a smooth, continuous speech signal. While the time domain waveform of the output may look different from the input, their frequency spectra are very similar, so the reconstructed sound is perceived as natural. Since only the filter coefficients and scale factor are sent, the required bit rate is much lower than that of the original audio. In practice, many refinements make this process more efficient and realistic. LPC codecs split speech into two parts: a spectral envelope, the overall tone shape, and a residual signal, the remaining fine details. The choice of codec depends on the application and desired bitrate. Conceptually, LPC models the human voice as a buzzer at one end of a tube. The buzzer represents the vocal cords producing vibrations, pitch, and loudness, while the tube represents the throat and mouth, creating resonances called formants. This model accurately captures vowel sounds but struggles with nasal or complex consonant sounds. Adding features like a nasal cavity branch can improve realism but also increases computational cost. The accuracy of LPC depends on the type of sound. Simple, periodic sounds like vowels are modeled well, but noisy or chaotic sounds, such as fricatives like S or F, and stops like T or P, are harder to predict. These hiss-like sounds require the encoder to distinguish between buzzing and hissing components. Some mixed or complex sounds, like certain nasal consonants or combined buzz-hiss tones, don't fit the LPC model perfectly, leading to estimation errors in the formants. In these cases, more information must be preserved in the residual signal. Good quality is possible if this residual is carefully coded, though it may reduce compression efficiency. The residual signal is created by filtering speech through an inverse filter. If the decoder received the full residual signal directly, it could perfectly reproduce the original speech, but that would require too many bits. Therefore, codecs compress the residual signal to lower the bit rate. The more accurately this residual is coded, the better the sound quality. Advanced methods like code-excited linear prediction, CELP, use stored codebooks to represent the residual more efficiently, producing higher quality speech at low bit rates compared to basic LPC. Code-excited linear prediction, or CELP, is one of the most common and successful speech coding methods used today. Though it began as a specific algorithm, CELP now refers to an entire family of related codecs. It is widely used in mobile communication systems like GSM, in internet telephony, and in software such as Windows Media Player. CELP's popularity comes from its flexibility and strong performance across many different bit rates. CELP builds on linear predictive coding, LPC, but improves it by using codebooks, collections of predefined excitation signals stored in both the encoder and decoder. The encoder examines the incoming speech, searches its codebooks to find an excitation signal that best matches the input, and sends only an index code that identifies this signal. The decoder uses the same index to retrieve the same excitation signal from its own codebooks and then passes it through a Formant filter that models the vocal tract. This process gives the method its name, Code-Excited Linear Prediction. CELP Codecs combine several powerful techniques within this framework. The encoder uses a closed-loop analysis by synthesis approach, where it tests candidate signals and compares them to the original speech to find the best match. To improve efficiency, it uses vector quantization, a method of compressing groups of parameters together. A key feature of CELP is perceptual noise shaping. Instead of treating all errors equally, CELP shapes the remaining noise so that it falls in frequency regions where the human ear is less sensitive. This is done using a perceptual weighting filter that pushes most of the error energy under louder parts of the speech spectrum, making the noise effectively masked and less noticeable. In some CELP systems, quality is enhanced by reconstructing harmonics that may have been lost during compression. Other systems extend narrow band signals into wideband ones by estimating the missing high-frequency content. During LPC analysis, wideband spectral envelope data can be stored in a secondary or shadow codebook. When decoding, this wideband envelope is merged with the narrowband excitation signal, improving clarity and producing a fuller, more natural-sounding voice. The CELP encoder models the human vocal tract using linear prediction and an analysis by synthesis approach to compress speech. It works by continually testing and refining its output to make the reconstructed, decoded signal sound as close as possible to the original. This process is done automatically and mathematically rather than by human judgment. The encoder divides the input speech into short segments and runs repeated searches inside a closed loop that includes a decoding stage. Each time, it compares the synthesized speech it generates with the original speech and calculates the error signal, the difference between the two. The encoder then adjusts its parameters step by step to minimize this error, creating the best possible match. To ensure that the system focuses on what matters most to human hearing, the error signal passes through a perceptual weighting filter that downplays spectral peaks. This prevents loud frequency areas from overpowering the optimization process and leads to a more perceptually accurate result. The CELP decoder acts like a speech synthesizer. It reconstructs speech by combining the parameters it receives from the encoder, such as gain, pitch, and delay, with the linear predictive coding (LPC) coefficients that represent the shape of the vocal tract. The decoder uses the codebook index sent by the encoder to locate the correct excitation signal, a residual signal that mimics vocal cord vibrations. This excitation is then passed through a Formant filter to shape the sound according to the encoded parameters, and then through the LPC filter to produce the final speech output. The decoder continuously predicts each new speech sample using a weighted combination of previous ones. While some prediction error always exists, the goal of linear prediction is to find the most accurate coefficients to keep that error as small as possible, resulting in clear and natural-sounding synthesized speech. In CELP and other linear predictive codecs, the encoder creates a residual signal, the difference between the original speech and its predicted version. If this residual were sent directly to the decoder, the reproduced speech would sound identical to the original, but the required bit rate would be far too high. To solve this, CELP codecs compress the residual signal at a lower bit rate. The closer this coded version is to the original residual, the better the codec sounds. CELP achieves this efficiency and quality using codebooks, large tables of pre-computed excitation patterns, each identified by an index code word. The encoder compares its current residual signal with all the stored excitation patterns in the codebook and chooses the one that best matches it, producing the smallest quantization error. Instead of transmitting the entire signal, the encoder only sends the index of the chosen pattern plus a small amount of extra information. This approach keeps data rates low while preserving good sound quality. However, searching through a large codebook for every frame would require a huge amount of computation. To reduce this, CELP designs optimize how code words are organized and stored. One common technique uses overlapping codebooks, where entries share parts of the same memory array, cutting down both storage and processing time. In theory, an infinitely large codebook containing every possible residual would give perfect quality, but this is impractical. It would require too much memory, too much computation to search, and very long index codes. Instead, codebooks are trained statistically. Algorithms adjust the stored code vectors by repeatedly comparing them to sample speech data until the quantization error is minimized. To further simplify processing, CELP systems often use two smaller codebooks instead of one large one, a fixed and an adaptive codebook. The fixed innovation codebook contains predefined excitation patterns that represent random or non-repetitive sound components, such as unvoiced speech. It can also use vector quantization for added efficiency. The adaptive pitch codebook, on the other hand, handles periodic signals like voice sounds. It starts empty and gradually fills up with time-delayed copies of previously encoded excitation signals. By reusing these past excitations, the adaptive codebook efficiently models the repeating nature of voice speech, keeping quality high while using fewer bits. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Vector quantization, VQ, compresses data by encoding whole groups of values together instead of treating each one separately. By analyzing how the values in a group relate to each other, VQ can represent the group more efficiently than coding every value on its own. Rather than coding the actual signal samples, VQ usually encodes the parameters that describe those samples. In speech coding, for example, VQ is often used to efficiently encode line spectral frequencies, parameters that represent the shape of the vocal tract. This method is commonly used in CELP and many other modern speech codecs. Some speech codecs are designed to create embedded or layered data, allowing flexible sound quality and bit rates. Along with the main core data, the bit stream includes one or more smaller, lower-rate bit streams that can be separated and decoded individually. These extra enhancement layers can be added to the core layer to improve sound quality when bandwidth allows. A scalable encoder includes a core encoder inside one or more enhancement encoders, producing a multi-layer output. Each layer builds on the one below it, so higher layers can only be decoded if the lower ones are also available. Depending on the network conditions or available bandwidth, some layers can be left out. The number of layers and their bitrate increments determine how fine the quality steps can be. The decoder's output quality depends on how many layers it receives and how capable it is. Scalability makes the codec adaptable to different transmission speeds and device capabilities. It also enables upgrades or new features without breaking compatibility with older systems. On the internet, data is sent as packets. Each packet includes header information and a payload that holds one or more frames of speech. In scalable VoIP systems, these layers must be clearly separated and easy to extract. For streaming, many frames can be packed together for efficiency, but this increases delay and sensitivity to packet loss. For real-time conversations, fewer frames per packet are used, and all embedded layers are kept within the same packet. The payload marks the different layers of each frame. The transport protocol must recognize and support these hierarchical layers, as well as prioritize the most important data for reliable communication. Bandwidth extension BWE is used to make speech sound clearer in audio codecs. It works by adding extra information to a narrowband NB signal, turning it into a wideband WB signal with more frequencies and better sound quality. This added data is small, but makes a big difference in how natural and detailed the audio sounds. Sometimes it can even create a super wideband signal by adding higher frequencies, which helps make speech more understandable, especially for distinguishing sounds like F and S. Many BWE systems are also backward compatible, meaning they still work with older narrowband systems. BWE in speech codecs is similar to spectral band replication, SBR used in music compression. However, BWE can use signal models of how speech is made, while SBR cannot. BWE can be added in different ways, only on the receiver side as post-processing, or in the network using a transcoder, both without sending extra information from the source. In speech BWE, the narrowband signal is analyzed to estimate what a wideband version should sound like. This uses a source filter speech model, which represents how the vocal cord source and the vocal tract filter produce speech. The bandwidth of the source excitation signal can be increased by adding harmonics through distortion, filtering, or other synthetic methods like mirroring or frequency scaling. Features from the narrowband signal are also used statistically to estimate the spectral envelope, the shape of the sound's frequency response, which is crucial for improving sound quality. Sometimes BWE data can be hidden in the narrowband signal using watermarking. This lets old systems play the sound normally, while newer systems can extract the hidden data to enhance quality. The watermark must be inaudible and not reduce speech clarity, even if the BWE data isn't used. It must also be strong enough to survive the full transmission chain, including processing and errors, while staying lightweight in computation and delay. A watermarking system must analyze the narrowband signal to find safe places to hide data without being heard. This can be done using perceptual analysis to find masked regions, or linear prediction to shape noise. Methods like spread spectrum and dither modulation are commonly used to embed the watermark securely and invisibly. Codec performance can be improved by reducing distortions like echo and background noise. Echo cancellation deals with a major problem in speech communication: acoustic echo, which happens when sound reflects off surfaces and returns with a delay. This echo can be clearly heard and is especially common in hands-free systems, where the loudspeaker sound leaks into the microphone. Echoes can also happen due to electrical feedback. Both types, if delayed, can be distracting and make speech harder to understand. Different methods exist to reduce echo effects. One simple method is voice-controlled switching. When sound is detected from the far end, the microphone level is lowered. When local speech is detected, the loudspeaker level is reduced. However, this creates half-duplex communication, only one side speaks at a time, and can cause unnatural noise changes, which can be masked with comfort noise. Another method uses echo suppressors that detect and block echo signals by inserting loss or temporarily cutting the line. But errors can occur if the speech is too quiet or the echo too loud. A more advanced method is adaptive echo cancellation. Instead of breaking the communication path, it creates a synthetic echo from the loudspeaker signal and subtracts it from the microphone signal. An adaptive filter continuously adjusts to model the echo path and generate the replica. The cleaner signal is then sent out. The main challenge is accurately matching the real echo path. Small differences leave residual echoes. Adaptive algorithms adjust filter coefficients step by step to find the best match. Examples include delay coefficient methods, double talk detection, remote single talk detection, two-path echo models, and dynamic regularization. Small adjustment steps improve precision, but react slowly to change, while large steps adapt quickly, but may become unstable in noisy environments. Some systems solve this by varying the step size or memory dynamically. Voice-controlled switching and adaptive cancellation can also be combined for better performance. To further reduce leftover echoes, a frequency-selective adaptive post-filter can be applied. It works like a noise suppression filter, using the power spectral density, PSD, of the residual echo to remove remaining artifacts. However, estimating the residual echo PSD is hard, especially when background noise is present. For background noise reduction, the system can capture noise during speech pauses and use it to build a noise profile, PSD. During speech, it can assume that some frequency bins, especially lower ones, contain only noise. The noise spectrum can then be estimated for those bins. This works because speech changes more quickly over time than most noise, even when the noise itself is not constant. Voice activity detection, VAD, checks the incoming signal to see if it contains speech or just background noise. When no speech is present, the system either uses the lowest bitrate to code the background noise or switches to a silence compression mode. During these silent periods, the decoder can create comfort noise to make the signal sound natural. VAD can work automatically in variable bitrate mode or be used separately in constant bitrate mode. If the background noise is steady, discontinuous transmission, DTX, can stop sending data entirely, further reducing the bitrate. In some applications, like voicemail, a variable bitrate VBR can be used to improve efficiency. Unlike a constant bitrate, VBR changes the bitrate based on the complexity of the audio. Complex sounds need a higher bitrate, while simple sounds can use a lower bitrate. This helps reduce the overall bitrate while keeping good audio quality. However, VBR can sometimes cause short-term spikes in bitrate or make the average bitrate higher than desired for very complex audio. Many codecs solve this with an average bitrate ABR feature, which sets a target average bitrate and adjusts the VBR in real time to meet it. Using ABR may slightly reduce the overall quality compared to a perfectly optimized VBR. Many speech recognition systems work by analyzing short-term features of speech, often using cepstral analysis. Some systems use statistical methods instead. However, background noise and echoes in a room can reduce recognition accuracy. In a speech recognition system, the speech signal first goes through front-end processing, where short-term spectral analysis extracts key features. The signal spectrum is converted into the cepstral domain to get mel-frequency cepstral coefficients, MFCC. Besides these static features, dynamic features can be calculated by tracking changes over several frames, known as delta, first derivative, and delta-delta, second derivative coefficients. Sometimes the front end also includes noise reduction and blind equalization to improve the signal before recognition. The Speex Speech Codec is used in VoIP, streaming applications like teleconferencing and video games, and file-based audio reduction such as podcasts, but not for mobile phone networks. It is open source and free to use, unlike many speech codecs that require patent licenses. Speex can be licensed under the BSD license and follows the same design philosophy as the Vorbis audio format. Speex is based on CELP coding, which makes it resistant to lost or corrupted packets, important for VoIP over UDP. It supports multiple bit rates, and the same bit stream can include narrowband and wideband audio. Speex also offers features like dynamic bitrate switching, variable bitrate, voice activity detection, and intensity stereo coding. The codec's delay equals the frame size plus the time needed to process each frame. The quality of speech coding systems is often measured by having people listen and evaluate the sound. Speech codecs are generally grouped into two types: wideband codecs and narrowband codecs. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.